Hey guys, today we're starting our last topic, which is over magnetic flux and the two laws that are going to accompany it. This is a pretty cool thing. It's a little abstract, but let's just go ahead and get right into it. So yesterday we had a lecture about induction, and at the beginning of that lecture we talked about Faraday and how he discovered that moving a magnetic field around a circuit could induce a current, which we then kind of ignored and just said we've got a moving bar on some rails and let's see what the EMF and the current are. But today we're going to be taking that application of Faraday's experiments and looking at them a little bit more closely. And the way that we are going to be looking at them is through the lens of magnetic flux. Flux is that F-L-U-X word right there, and it means the amount of magnetic field passing through a region. I couldn't find a great picture, so I'm going to draw one. This is going to be like a circuit, okay? And we'll have some field. This field is coming out of the page. And we're going to assume it's a uniform field going everywhere around here. All right, ignore my crappily drawn field. So we've got a circuit in this magnetic field. Magnetic flux is the amount of field that is contained inside the region of the circuit. So all of that field that's going through there is the magnetic flux. And really, I like to think of this in terms of the units, because the units really, enlighten the situation. The unit is Weber, W-E-B-E-R, but that is defined as 1 Tesla times meters squared. Tesla is the magnetic field strength, and meters squared is an area. So it's like the field over an area. And there's 3 things that are going to affect the magnetic flux. That is how strong the magnetic field is. If you've got a really strong field, it's going to have more flux. The area of the loop that you're observing. So if you got a bigger area, it obviously incorporates more field inside it. And then also the angle between the loop and the field, which we'll see over the next few slides. All right, so we understand field and area. Those are pretty obvious, but the angle is going to be a little bit different. And the way that the book asks you to imagine it is with a fan. So a fan blows air. And if you have a loop that is in the path of that air, the air goes through the loop, which makes sense. But if the loop rotates, it has less air going through it. So if you had the loop sitting at 90 degrees, like this being the side of the loop, the ends going into the page, you'd have a lot of air flowing through that loop. But if instead the loop is at an angle, like this, that same area of loop doesn't quite cover as much of the flow of the fan, so it has less of the air flowing through it. So if you tilt the loop, it's going to have less flux going through it than if the loop is at 90 degrees to the field. And you can see that again here in a picture that's drawn better than my picture. As you tilt the thing, it covers less field lines, so there is less of the field or the air in the analogy going through the loop, even though the loop hasn't actually reduced in size. What happens is that as it is tilted, it covers less of the field, so its effective area is going to get smaller. These are the same loop. This one is just tilted. So to incorporate all 3 of those factors, we had area, field, strength, and the angle. We have this equation that says the magnetic flux. Flux is this capital phi. That is the magnetic flux equals the area dot the B field. This dot is a dot product. We looked at cross products earlier in the unit. Cross products are multiplying vectors and getting a vector product. Dot products give you a scalar. So you'll take the area vector dotted with the B field vector, and that answer will give you a scalar. That the dot product can also be defined as the two things put together times cosine of the angle between them, which is this right here. So we can see that each of the factors is taken into account. We're taking into account the area of the loop, the strength of the field, and the angle between the two. Now you may have a red flag raised here when I say the area, and you think, how can area be a vector? How is the vector direction of area defined? And the direction of the area is, say this is my area lying flat in the plane of the page. The vector direction of that area is a vector perpendicular to that area. So this one would have a vector defined coming out of the page. And that's not super well defined because you could also have one going into the page, but we're going to ignore that right now and just say the direction of the vector is perpendicular to the plane of the area. So if you've got the magnetic field, which I'll make blue here, coming out of the page, and the area vector coming out of the page, that means the loop is perpendicular to the B field. Then you've got cosine of the angle between the area vector and the B field vector, which they're both pointed in the same direction. So you'll have cosine of 0. Cosine of 0 equals 1, and you'll have a maximum amount of flux. So that makes sense. All right, let's look at this question as a conceptual example for what we're talking about. We're looking at this one up here where the field is twice as strong. So if the field is twice as strong, the flux should increase by a factor of 2. I'll do increase times 2. Okay, and then down here for the bottom one, for B, the square is twice as wide. Now flux increases with area, so if the square side is twice as wide, it should increase by a factor of 2 squared, which is 4. So B should be the correct answer. Loop B has a larger magnetic flux. All right, for this one, we've got a metal loop being pulled through a uniform magnetic field. Is the magnetic flux through the loop changing? So there's 3 factors that can change the magnetic flux. You can either change the B field, the area of the loop, or the angle between the two. And here, we don't have any of those things changing. The B field is staying constant. Velocity is not one of those factors. Area of the square isn't changing, and the angle isn't changing, so no, there is nothing changing. And this makes sense if you did one of your homework problems on the front page. I think it was the middle one on the left. It kind of touched on this concept. We do have these 2 bars that would be experiencing some magnetic forces. You'd have the positives all drawn towards this end, or one end, let's see. Got to do the rule to figure it out. They're going to be drawn towards the bottom. My bad. So we got positives being drawn to the bottom and negatives being drawn to the top. Well, you've got a low potential on each end of these bars at the top and high potential on the bottom side. So between the highs and between the lows, nothing's going to flow because there's not a potential difference. So the charge distribution of this square is going to change, but the actual magnetic flux through the loop does not change. All right, and last one, the metal loop is rotating in a uniform magnetic field. Is the magnetic flux through the loop changing? Well, you got to ask your 3 questions. Is the B field changing? No. Is the area of the loop changing? No. Is the angle of the loop changing? Heck yeah, it is. It is rotating. So if the angle changes, the magnetic flux does change. The answer is yes. All right, here we go with an actual math example. At a particular location, the Earth's magnetic field is 50 microtesla, tipped at an angle of 60 degrees below the horizontal. So let's make this the horizontal. And Earth's magnetic field is at 60 degrees below that. So I'm going to draw some field lines. I probably should have drawn them in a different color. Oh well. A 10 centimeter diameter circular loop, I'll make that thing red, sits flat on a table. So the flat loop is going to look like this. Flat loop. What is the magnetic flux through the loop? So what we need here, and this one is going to be a wee bit tricky, a little bit. What we need here is the flux, which equals area dotted with the B field, which is equal to the A, B, the magnitudes multiplied together times cosine of the angle between them. Now this one is not quite plug and chug for one simple reason. This theta is the angle between the area vector and the B field vector. But the area vector is going to be perpendicular to that loop. Perpendicular to that loop is right here or right there, either way. So that angle between the two is not going to be 60 degrees. It's going to be 90 minus 60 degrees, so 30. So you need to make theta 30 degrees. Always check your area vector before you just plug and chug. Make sure you're using the correct angle. And then we'll also need the area. We've got a 10 centimeter diameter, so that's going to be a 5 centimeter radius. Area equals pi times the radius, 0.05 squared. And the B field is given as 50 microtesla. So then you can plug and chug now that you know the angle and the area. You say magnetic flux equals pi 0.05 squared times 50 micro is times 10 to the negative 6th times cosine of 30. And you should type that into a calculator, get an actual number. The answer will be in Webers, but I am not going to do it right now because it's late and I'm tired. You should type it in. This is the correct setup. You should get some answer in Webers. Also note, it is really considered bad practice to do all of this math without units, but I do it without units all of the time just because I don't want to deal with it. So eventually you should start using units and convince yourself of that. Don't follow my example there. Do as I say, not as I do. I'm not counting points off on it for anything, but really it is good practice to include your units to make sure all of your math is working out correctly. All right, so where we're going today with this idea of flux, the reason that it's important is because it's going to help us with some rules for determining current in a loop. And there are 2 laws that use flux to determine the current in a loop. The first one is Lenz's law, which will tell us the direction of the current. And the second one is Faraday's law, which will tell you the numerical value of the current. So we're going to have to use both of them to determine current in a loop. So the first law there was Lenz's law, and Lenz's law, which I'm going to read in 2 parts, says that there is an induced current in a closed conducting loop if and only if the magnetic flux through the loop is changing. So in order for a current to be created in a conducting loop in a magnetic field, either the field strength has to be changing, the loop size has to be changing, or the loop angle has to be changing. Note, if any of those 3 things is changing, you've got a current. If none of those 3 things is changing, you don't have a current. And then Lenz's law also says that the direction of the current is such that the induced magnetic field opposes the change in flux, so overall flux stay constant. That sounds like a bunch of gibberish probably, so we're going to explain it in pictures. All right, so we're going to look at this picture here. You've got a loop of wire that has an area, and it's in a magnetic field. While the magnetic field is sitting there, the field lines are going through the loop, and it has some flux, which we'll call flux initial, flux I. Ignore my poorly written phi. All right, and while the magnet's just chilling there, we're not moving it, the flux isn't changing because the angle is not changing, the amount of field going through is not changing, nothing's changing. So there is no current, as you can see in the lovely ammeter right there. However, in this picture, which shows quite a bit, if you move the magnet downwards through the coil, that's going to change the field strength inside the coil. So field strength is going to be changing. And as the magnet moves down, the field strength increases, so the flux also increases. That's the flux from the magnet increases as you move the thing down, because you're getting more field going through the loop. Sorry, it's late, I can't think of words. Now, Lenz's law says that a current will be produced because the flux is changing. But the current can go one of two ways around this loop. It could either go clockwise or it could go counterclockwise. So the second half of Lenz's law is going to dictate that direction. It says that the induced current will create a magnetic field that opposes the change in flux. So if the magnet moving makes the flux increase, the current's going to try to make the flux decrease so that it evens out to be the same flux as you had originally. So we're going to try to create a field to decrease that flux. And to decrease that flux, you have to create a magnetic field going backwards through the loop. So if the field created by the original magnet goes down, I'm going to draw that in, oh, there's a lot of blue there. I'm going to draw it in green. The original magnetic field is going down. The magnetic field that is induced by the current in the wire is going to go up to oppose that. So that instead of having larger B field vectors, you'll have the same B field vectors as you did previously. And then you can use right-hand rule for currents to figure that out. You put your thumb in the direction of current, say we'll make the current go clockwise. If you make a current go clockwise around this loop, in the middle of the loop, your fingers point down, which is not the direction we wanted the field. We wanted the field to be up. So let's switch to counterclockwise. If you go around the loop counterclockwise with your thumb pointed in the direction of current, you'll get that the field in the middle of the loop goes up. So you know that the correct direction for the current is counterclockwise. Now, conversely, if we said the magnet is moving upwards, that means the flux through the flux through the loop is going to be decreasing because we're going to have less field going through the loop. So in order to counteract the phi decreasing from the magnet, we're going to try to make the phi increase with the current. So I'll do this as a C for the current. So we're going to want more downward field in order to increase that flux. So you're going to need more downward field produced by the current carrying loop. To create a field that goes downward in the middle, you need a current that goes clockwise. So that's going to be opposite the direction we had in the previous question. So if the magnet is going down into the loop, it generates a counterclockwise current. If it's coming out of the loop, going up, it creates a clockwise current. And that is Lenz's law. It just determines the direction of that current. So let's look at a couple of examples here. It says the bar magnet is pushed toward the center of a wire loop, which is true. There's a clockwise current, there's a counterclockwise current, or there is no induced current. Well, let's see if there should be current. Is the magnetic field strength changing? Yes, because as you get closer to the magnet, the field strength gets larger. Cool. So there is no induced current, cannot be correct because flux is changing, therefore there is an induced current. Now, as the bar moves, what happens to phi? It should increase. The phi from the magnet should increase. In order to counteract that, to balance it out, the phi from the, or the field from the wire. Wow, I am just really struggling with words. The field from the current carrying wire has to counteract that increase in flux, so it's going to create a reduction in flux. In order to decrease the flux with using the wire, you're going to have to generate a B field that counteracts the increasing B field. So if the B field is going to get stronger pointing up, we need a B field to counteract that points down. To have a field pointing down in the center of the loop, you need a current that is going clockwise. So that is A. All right, let's look at this example. A loop is moved towards a current carrying wire as shown in the figure. As the wire is moving, there is a clockwise current around the loop, a counterclockwise current, or no current. No current. So let's look at the field here. All right, so we've got a current carrying wire with current going to the left. You use the right hand rule to say up here in this top region, you've got magnetic field going into the page. And right here close to the wire, the field strength is greater. Let's see. I'm going to try to indicate that here. Cool. I have drawn my field. And the wire is moving towards the loop. So as the wire moves toward, the loop is moving towards the wire. As the loop moves towards the wire, what happens? Well, it gets into a region of greater field. So there is a change in flux, which means current has to be flowing. So no current is not an option. Now, as the loop approaches the wire, its magnetic field strength increases. So it needs to, the loop is going to produce a field that is going to counteract that. So if the field is increasing in strength, the loop produces a field going opposite of that so that it'll subtract. So we're going to have a field produced by this loop going or coming out of the page. Cool. Ignore the crappily drawn field yet again. So to produce a field going into the page, this loop would have to have current going, let's see, into the page. Use the right hand rule. It's going to be going clockwise. All right, and Faraday's law is a lot simpler than Lenz's law. Faraday's law says that the EMF of the circuit, which would, according to Ohm's law, equal I times R, equals the, oh, rip, this should be change in magnetic flux. I need to go change that for my slides. It should be change in magnetic flux over change in time as an absolute value. That is the EMF produced by the circuit. And if you've got a coil going through, it's N times that, because you've got basically a bunch of little areas stacked all on top of each other. So we're going to look at that here. We've got 3 different scenarios, A, B, and C. Let's look at A first. A has a 10 centimeter diameter loop in a magnetic field with a resistance of 0.1 ohms. Find the magnitude and direction of the induced current. So for A, we know that the field's going into the page and this field strength is increasing at 0.5 teslas per second. If the field strength is increasing, that means that the current carrying wire is going to produce a field that will change that will counteract that. So it's going to need to produce a field going opposite of the current field. So going into the page. To produce a field going in the middle there into the page, you would need a current that is going around the wire clockwise. So we know the direction according to Lenz's law, and then we can find the magnitude according to Faraday's law. Faraday's law says that the EMF equals change in flux over change in time. And flux, remember, is A, B cosine of the angle between them. Here they're at, or they're parallel. You've got the area angle, which is perpendicular to the actual surface. The surface is perpendicular to the field, so therefore those two things are parallel. So sine is going to, or not sine, cosine is going to be 1. So you just get A times B, area times B divided by delta T, which equals current times resistance. So area of the loop, I'll make up here, area equals pi times the radius squared, the radius 0.05 squared, which is the same as the previous question we were looking at a while ago. And then B is increasing at 0.5 teslas per second. So that is this little rate right here. You've got area is pi 0.05 squared. And then B divided by delta T is this 0.5. And that equals current times resistance, which is 0.1. So you can math that out to find I, the induced current going clockwise around that circuit. Now over here on the other side, we should see that if the field is decreasing, that means Lenz's law is going to create a field going in the same direction as was already here. And if we're going the same direction as was already here, we're going into the page, which is the same direction as the previous question, or part A. So we got clockwise. And the flux here, we've got EMF equals change in flux over change in time, and actually that's absolute value. So we get A is the same thing, B over delta T equals IR. B over delta T is still 0.5 teslas per second. It is negative, but we got the absolute value, so it doesn't matter. So you're still going to get the same induced current as you did from part A. Same thing. And lastly, part C. For part C, the field is decreasing at 0.5 teslas per second, but if you look at the angle between your area here and your field, you'll see that there is no flux going through that loop. Therefore, your current is going to be 0. All right, so that's almost all for lecture today. There's one slide we're going to look at, which was actually from a previous part of this unit, or actually it's just from yesterday. And we're going to see how all this stuff applies to the circuits we were looking at yesterday. So this is one of the circuits we were looking at yesterday. We had the moving bar on the conducting rails. And a current is induced. That's what we saw yesterday. So the reason that this current is induced is because this bar is moving, and as the bar moves, the area of this loop decreases. So if the area of the loop is decreasing, the flux through the loop is also decreasing. So Lenz's law states that the circuit's going to try to counteract that. So to counteract a decreasing flux, it's going to increase the field strength. And we know in this circuit, the current is flowing clockwise. If the current is flowing clockwise, that means it is creating a field going into the page everywhere in this region. So that's the field produced by the current. And we said the field produced by the current has to supplement or add to the field of the region in order to counteract that decreasing flux. So the field the external field has to be the same direction, which means it'll be into the screen, which is the same thing we got yesterday when dealing with the induced charges in this bar. So this is consistent with what we learned yesterday, and it's actually a little bit more applicable to some of the more complex circuits that aren't as straightforward as a bar sliding on a rail. All right, guys, thanks for watching. Test, I'm recording this before the polling results are in, so test will either be this Friday or it will be not next Tuesday, the Tuesday after fall break, whatever you and your classmates decide on. So if you've got questions, please ask them. Please let me know.